We'll be talking about auxiliary equations with complex roots. So let's take a look at our linear differential equation. And this is a second order differential equation. So we have our second order linear differential equation. And as you can see here, we have our constant coefficients. And in previous lessons, we talked about the auxiliary equation that can be written as AR squared plus BR plus C is equal to 0. And when we looked at the solutions of that auxiliary equation, we came up with either two distinct roots, which were real, or one repeated root, which was also real. How did we do that? Well, there are three cases, and we've talked about two for our solutions. So we take a look at what we call the discriminant. And that discriminant gives us the number and type of solutions that we will have. So in case number 1, if the discriminant is positive, we will have two real distinct roots. And in that case, our solution looked like this. Y of t equals C1 e to the R1t plus C2 times e raised to the R2t. And those two real roots, let me move this over, those two real roots were R1 and R2. And then we wrote our solution. The second case is when we come up with the discriminant equal to 0. And in that case, we had one real repeated root. And in that case, we just called that root R1. Actually, we could just say R. So our solution that we had looked like this. C1 e to the RT plus C2t e to the RT. And then now this is what we're going to be looking at in this video. And that is the case where the discriminant is less than 0. And in this case, we are going to have two complex roots. We will have an imaginary part of that. We call those a complex pair. And that's what we are going to be talking about in this video. Okay, so let's take a look at what we have. When we solve this auxiliary equation, and we have it right up there, AR squared plus BR plus C equal to 0. We just have a quadratic. We say that R is equal to the opposite of B plus or minus the square root of B squared minus 4ac all over 2a. So we could say that we have our two roots as the opposite of b over 2a, and we could say that we have our second root. Actually, let's just go ahead and simplify r and share that denominator. So we would have the real part, and then we could have this imaginary part. Let's look at it that way. Okay, so what do we want to do? Let's go ahead and call this expression alpha and this expression beta. And so what we would have would be a solution that looks like this. Y of t is equal to c1 e to the alpha plus I beta. And I have to do one thing here. We know that this is the real part, and this is the imaginary part. Okay? But what we could do is we could rewrite this as the opposite of b over 2a plus or minus I times the square root of, and if we use 4ac minus b squared all over 2a, this would now be a real number that we could call beta. This is a real number that we could call alpha. And of course, we still have our I. So we could say that we have alpha plus or minus I beta. And that's what leads us to this solution. And now we can write this as C1, our solution as C1 e to the alpha plus I beta t. And as you can see, we will have plus a second constant multiplied by e raised to the alpha minus I beta t. And those are our two r values there in the exponent. Okay, so let's go ahead and think about this. Here we have some imaginary numbers in the exponent. And we would like to have real numbers in our exponents. Whoops. So, what we will do is now go ahead and take a look at just this y1 of t. So if we look at y1 of t, we could say that that's e to the alpha plus I beta times t, which is equal to e to the alpha t multiplied by I beta t. And as you can see, this is real. And this, we can go ahead and use Euler's formula to simplify. Okay? So now we can say that we have e to the alpha t multiplied by the cosine of alpha t. Whoops. Cosine of beta t plus I sine of beta t. And you can remind yourself of Euler's formula, which means that we will have y2 of t equal to e to the alpha t, and this time we will have the cosine of beta t minus I sine of beta t. So in this case, we still have imaginary numbers. So we want to consider y1 plus y2 over 2, and we will come up with e to the alpha t times the cosine of beta t. And this is entirely real. This is all real. And so that's how we will also consider y1 minus y2 of t, and we will come up with, divided by 2I, and we will come up with e to the alpha t sine of beta t. And again, we have all real values. Therefore, we finally come up with a combination of these two solutions. So we have two solutions. They're both real. They're both linearly independent. They're not a multiple of each other. And we come up with y of t is equal to c1e to the alpha t cosine of beta t plus c2 e to the alpha t. Ran out of room just a little bit. Let's see if I can bring this down over here and go ahead and move some of this over just a little bit. Okay, and cosine c2 e to the alpha t sine of beta t. And there we have our solution, and these are our complex pair of roots. So let's go ahead and give this a try. So this is what we will be using. I can actually make that just a touch bigger. Okay, and let's go ahead and look at our first example. Find a general solution to the differential equation shown below. So we come up with our auxiliary equation, which is going to be r squared minus 10r plus 26 is equal to 0. And we have roots r is equal to 5 plus or minus I. And I'll go ahead and show you on this first one what we have there. So we have r is equal to 10, the opposite of b, plus or minus the square root of b squared minus 4 times 26 all over 2. And we come up with 10 plus or minus negative 4 over 2, which is 5 plus or minus I. And I could go ahead and put this 10 plus or minus 2I over 2, 5 plus or minus I. Okay, so now let's go ahead and write our solution. So alpha is equal to 5 and beta is equal to 1. So therefore, y of t is equal to c1 e to the 5t times the cosine of beta t, which is just t, plus c2 e to the 5t multiplied by the sine of t. And this is our general solution. Okay. Let's take a look at our next example. We will go right to our auxiliary equation, and that is 4r squared minus 4r. Well, we should first simplify this equation, and of course we have 2y double prime minus 2y prime plus 13y equals 0, removing that common factor. So our auxiliary equation is 2r squared minus 2r plus 13 equal to 0. And we have that r is equal to 2 plus or minus the square root of 4 minus 4 times 26 all over 2. And that will give us 2 plus or minus 10i over 2, and we get 1 plus 5i. 1 plus or minus 5i. And so, therefore, we have alpha equal to 1 and beta equal to 5. Let me move that down here. And so our solution is y of t, c1 e to the t, cosine of 5t plus c2 e to the t multiplied by the sine of 5t. And that is our general solution. Okay, let's take a look at our next example. Find a general solution to this differential equation. U double prime plus 7u equals 0. So our auxiliary equation is r squared plus 7 is equal to 0. And so our roots are r equals plus or minus 7i. Let me just go ahead and write that out. So we have r squared equals negative 7. So r equals plus or minus I root 7. So we have alpha equal to 0 and beta equal to root 7. So our general solution is u of t equals c1. And then, of course, we would have e to the 0t multiplied by the cosine of root 7 times t plus c2 e to the 0t sine of root 7 multiplied by t. And that simplifies to c1 cosine of t root 7 plus c2 sine of t root 7. Okay, let's take a look at our next example. Find a general solution to this differential equation shown below. We will come up with our auxiliary equation. So we have 2r squared plus 13r minus 7 equals 0. We have r equals the opposite of 13 multiplied by the square root of 169 multiplied by 2 and negative 7 all over 4. Now, as you can see here, we are going to have real roots. So, taking a look at these, we can go ahead and simplify this and have negative 13 multiplied by the square root. And I see that I forgot that 4 here. Minus 4 times 2 times negative 7. And that comes up to 225 under that root. All over 4. And simplifying. And I could have written that over to the side. But as you can see, we come up with, and boy, I really did a number here. Move that over. Move that over. Move that over. Okay. Back on track. Back on track. Back on track. So now we have negative 13 plus or minus 55 over 4. Boy. Boy, oh boy. Let's just change these. And of course, you can see that we come up with 1/2 and a negative 7. Whew, that was a lot. So now what do we have? We have alpha. Excuse me, we do not have alpha and beta. We have 2 real distinct roots. And we have our solution. Y of t is equal to C1e to the 1/2 t plus C2e to the negative 7t. Well, finally finished that problem. Okay, let's take a look at our next example. Here we have a third order differential equation. So let's just proceed in the same manner with our auxiliary equation, r cubed plus r squared plus 3r minus 5 equals 0. So by inspection, we can sort of see that r equals 1 satisfies the equation. So that will help us find that quadratic multiplied by that binomial factor. So we'll go ahead and use synthetic division, and we see that this quadratic factor is r squared plus 2r plus 5. And so now we can find our 2 other roots. So our first root, let me go ahead and write that down. We have r equals 1 is a root, and now we'll go ahead and find our other root. So we have r, and we have negative 2 plus or minus the square root of 4 minus 4 times 5 all over 2. And we come up with negative 1 plus or minus 2i. So our general solution will look like this. And of course we have alpha equal to negative 1 and beta equal to 2. So our general solution will be y of t equals C1 e to the t, which comes from that root. And now we'll go ahead and add that to C2e to the alpha t multiplied by the cosine of beta t. And now we have our third constant, e to the negative 2 sine of 2t. Okay, let's take a look at some initial value problems. Solve this initial value problem. It's a second order differential equation, and we were given an initial condition for y and also y prime. So we come up with our auxiliary equation, r squared plus 2r plus 17 equals 0. I'll go ahead and let you do that work. And we come up with r equals negative 1 plus or minus 4i. So our general solution is y of t. Of course, we have alpha equal to negative 1. So we would have c1e to the negative t multiplied by the cosine of 4t plus c2e to the negative t sine of 4t. So we have our arbitrary constants, c1 and c2, and now we are going to have to see if we can satisfy our initial conditions. Before we do that, why don't we go ahead and find y prime of t, and y prime of t, we are going to have, let's move that up here. And so we will have y prime of t multiplied by a negative 4. Put that negative 4 there. Plus, and that would be a minus, negative c1e to the negative t cosine of 4t. And now let's work on the next one, the next term, plus c2e to the negative t multiplied by 4 cosine of 4t, plus, and that would be a minus, c2e to the negative t sine of 4t. So let's see if we can simplify that a little bit, and we could go ahead and factor out a c1 e to the negative t. And what you'll see we'll have left would be the negative cosine of 4t minus 4 sine of 4t. And we could go ahead and move that over just a bit. And we'll do the same thing. We'll go ahead and factor out a c2e to the negative t. And you can see we have the opposite of the sine of 4t plus 4 cosine of 4t. So we were given these two initial conditions. So we could see that y of 0 is equal to c1, which is 1. And we can also see that y prime of 0 is the opposite of c1 plus 4c2. And so you can see here that c1 is 1 and c2 will be equal to 0. So our solution is given as y of t is equal to e to the negative t multiplied by the cosine of 4t, since we have c of t equal to 0. And that's our solution of the IVP. Okay, let's go ahead and take a look at our next IVP. And our auxiliary equation is r squared minus 4r plus 2 equals 0. And r is going to be equal to 4 plus or minus 16 minus 4 times 2 all over 2. And we end up with 2 plus or minus root 2. Well, these are real numbers. So we can go ahead and write our solution as y of t equal to c1 multiplied by e to the 2 plus root 2t plus c2e to the 2 minus root t. And of course, we have our arbitrary constants c1 and c2. So now we want to go ahead and take a look at our initial conditions. And we can see that we have y prime of t equal to 2 plus root 2 c1e to the 2 plus root 2t plus 2 minus root 2 c2e to the 2 minus root 2t. So if we want to go ahead and use our initial conditions up here, you can see that w of 0, which is equal to 0, is equal to c1. So that would go and that would go. So we have that's equal to c1 plus c2. I'll just put that that's equal to 0 there. So we know that c1 is the opposite of c2. And then we can do the same for w prime of 0. And we can say that that's 2 plus root 2 c1 plus 2 minus root 2 c2. And of course, that's going to be equal to 1. And what I might do is go ahead and change this color to maybe a green, okay? And that way you can see how we were finding those. So putting those together, putting these together, you will see that C1 is equal to root 2 over 4, and C2 is the opposite of root 2 over 4. So we can go ahead and write our desired solution. So we have WT equals root 2 over 4, e to the 2 plus root 2t minus root 2 over 4 multiplied by e to the 2 minus root 2 multiplied by t. And if you'd like, you can go ahead and factor that root 2 over 4 out. It makes it kind of nice. We have e to the 2 plus root 2t, and then we have minus e to the 2 minus root 2t. And that is our solution to that IVP, our particular solution. Okay, let's take a look at our next example. We have the initial condition shown and our second order differential equation. We can go ahead and write our auxiliary equation. We have r squared plus 9 equals 0, and we have r equals plus or minus 3i. So our general solution is y of t, and of course here we have alpha is 0 and beta is 3. So we have y of t is equal to c1 multiplied by the cosine of 3t plus c2 multiplied by the sine of 3t. We can go ahead and solve for our constants, but let's go ahead and find y prime first. So we have negative 3c1 sine of 3t plus 3c2 cosine of 3t. So going ahead and using our initial conditions of y of 0 equal to 1, we will have y of 0 equals c1 cosine of 0. So 1 has to be equal to c1. And then we have y prime of 0, which is also equal to 1. And that's going to be equal to 3c2. So c2 is equal to 1/3. So we can come up with our y of t. Our solution is the cosine of 3t plus 1/3 multiplied by the sine of 3t. Okay, let's take a look at our next initial value problem. And here you can see we have a third order differential equation. We could go ahead and write our auxiliary equation down. R cubed minus 4r squared plus 7r minus 6 is equal to 0. Of course, we have a cubic. You can look at your p over q's, plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. The p's come from that negative 6 and q comes from the 1, so that makes it nice. And upon further examination, you should be able to see that r equal to 2 satisfies this equation. So knowing that, we can go ahead and say that we have r minus 2 as one of our factors, and we can go ahead and put 2 in the box and use our synthetic. And here we have r squared minus 2r plus 3. Okay, let's go ahead. We already have 1. Go ahead and circle that. 1 solution. And now we'll go ahead and find the others. So we have r equals 2 plus or minus the square root of 4 minus 4 times 3 all over 2. And if you work that out, you'll get 1 plus or minus root 2i. Let me put that I in front. I root 2. So we have alpha equals 1 and beta equals root 2. So now we can write our general solution, which is y of t is equal to c1e. And let's go ahead and take this e to the 2t. Go ahead and take that, use that solution first. Plus c2 e to the t multiplied by the cosine of I root 2 plus c3 e to the t sine of I root t, root 2. See if I can bring that down just a bit. Okay. And now I can make that bigger. Okay, so now we will use our initial conditions, and we are going to need quite a few derivatives here. So we're going to need to get y prime and y double prime. I'll go ahead and give you these simplifications. So we have 2c1e to the 2t, and then we're going to factor out c2e to the t, and we will have the cosine of the square root of 2t. I'm seeing that I made a mistake and put an I here, and those should be t's. And then we have minus the square root of 2 sine of t root 2. Now we'll go on to the third term, c3 e to the t, and we have the sine of t root 2 plus root 2 multiplied by the cosine of t root 2. Okay, and I'll go ahead and give you y double. So y double prime of t is going to be 4c1e to the 2t. We'll go ahead and keep that c2e to the t factored out. And we have the opposite, the opposite of cosine, okay. See if I can move that down. So we have the opposite of the cosine of root 2t. I like to put that t in the cosine of t root 2 minus 2 root 2 sine of t root 2. And then here's our c3e to the t, and we have the opposite of the sine of t root 2 plus 2 root 2 cosine of t root 2. Okay, so using those initial conditions, which we have y0 equals 1, y of 0 equals 1, and we have y prime and y double at 0 equals 0. So putting these together, we have c1 plus c2 equals 1, and then we have 2c1 plus c2 plus root 2c3 is equal to 0. And now let's use the second derivative for c1 minus c2 plus 2 root 2 c3 is equal to 0. So putting that together, we have c1 equals 1, c2 equals 0, and c3 equals the opposite of 2. So with these values and these constants, of course you can see c2 is going to be equal to 0. And so that simplifies, and we get y of t equals e to the 2t minus the square root of 2, e to the t multiplied by the sine of t root 2. Okay,